We will use Roy Oswalt to demonstrate the power aspect. Roy is an excellent example to use because he doesn't possess some of the physical attributes that are often exhibited by power pitchers, namely body size. Roy Oswalt is 6 foot tall, 180 pounds, and throws 95 miles an hour. This is not a prototypical body size to throw that hard. As you will see, Roy uses his body efficiently to maximize his velocity. We will discuss the utilization of the backside. The backside is what we use the most to generate power in assisting natural arm speed. In addition to the backside, fast twitch type 2 fibers in the shoulder will play a large role in arm speed. By utilizing other body parts in sequence, we hope to achieve maximum arm speed with a minimum amount of effort. There is a key principle of sequencing. It's called the theory of addition, meaning adding body parts and their energy created in sequence. It is likened to the gears of a transmission. You will achieve faster speeds if you shift from first gear to second to third and so on. It is much more difficult if you started in second gear and shifted to fourth. If the gears are shifted in the proper sequence, then maximum efficiency and power will be achieved. The same principles apply to pitching. It would be more efficient to utilize my body and shift into the next gear along the kinetic sequence. The benefits of synchronizing the kinetic sequence will be that you will be able to repeat the delivery with maximum efficiency, thus enabling you to deliver a multitude of pitches and delaying the onset of fatigue. In addition, since the body is working in sequence, you will experience the sensation of achieving a maximum result with minimum effort. In other words, throwing harder, easier. We will use Roy Oswalt to demonstrate the power aspect. Roy is an excellent example to use because he doesn't possess some of the physical attributes that are often exhibited by power pitchers, namely body size. Roy Oswalt is 6 foot tall, 180 pounds, and throws 95 miles an hour. This is not a prototypical body size to throw that hard. As you will see, Roy uses his body efficiently to maximize his velocity. As he drives home, you can see his leg in a fully extended position with his arms starting to load as the hips rotate. When the hips rotate to the fullest point, his shoulder girdle will be in a cocked position or maximum external rotation. As I back it up, notice the forearm angle is greater than 90 degrees. This is not typically the ideal position to be in because of the added stress it adds on the front part of the shoulder and the propensity to drag the arms through the zone. However, Roy is able to overcome this because of how he can utilize his torso and close this angle on his leg. This position places him in an elongated position, putting his release point closer to home plate. By utilizing his torso, he can lower his release point and create more energy to help him propel the baseball on a downhill plane. If he was not able to do this, it would be a challenge to keep the ball down in the zone without diminishing his velocity. We will look more closely at the key principles as they occur in the delivery. We will now move to the first part of the delivery, where momentum and leg drive are used. We will use Roger Clemens in addition to Roy Oswalt to demonstrate varying techniques each pitcher uses to create energy. There are different ways that our models use to create momentum that will carry the bodies homeward to aid in the process of velocity. The purpose of each technique is to create energy by initializing the lower half of the body and transferring kinetic energy to the upper half of the body to achieve maximum velocity. As you can see, when they raise their legs, their bodies begin to move forward, initiating the process of momentum. Notice that Roy Oswalt carries his body forward in the glide. When he gets to knee lift position, his body has traveled far down the slope, building up speed before he separates his hands. His back leg will then kick into gear to accelerate his body even faster, generating more momentum. Roger Clemens accomplishes this as well, with a slight variation. His body is moving forward, and he actually shifts his weight on the front side as he picks up his leg. He will move forward, initiating momentum, before he shifts back onto his backside, accelerating his hips, thus increasing his momentum. He too will drive with his back leg and accelerate his body toward home, creating energy with his back leg. These are both excellent examples of how to generate velocity with momentum and leg drive. Once the body has been propelled forward by gravity and by the force of the back leg, then a degree of momentum has been created to help us create more power. It is now time to take the linear energy and transfer it into rotational energy by the rotation of the hips and torso. Energy created by the legs will continue up the kinetic chain to the hip and will begin the process of spinal rotation. As the spine rotates, it will connect with the shoulder and begin to move the cocked shoulder girdle. This will create a whiplash manner of the shoulder, building up torque before the shoulder releases. At this point, the shoulders have turned and are now parallel to home plate. The shoulder will have reached its maximum external rotation. While in external rotation, energy is stored in the shoulder by way of torque, thus creating a catapult effect. The acceleration process of the arm begins by the release of this torque. Torque can be defined as a measure of how much a force is acting on an object that causes that object to rotate. So the force that is applied to the hand, created by the leg drive, spinal flexion, and rotation, causes the arm to rotate in the shoulder, which is the pivot point. The faster the hand moves down, the more torque is put on the pivot point. Imagine, if you will, a catapult. The force that is applied to the end is multiplied at the resistant pivot point. The farther and faster the arm travels, the more torque is generated. Energy is stored by the resistance of the pivot point, or coiled spring, if you will. When the force is removed on the end, the energy that has been stored by the coiled spring will be released, and the arm will travel at a high rate of speed forward around the pivot point. If you take this torque energy and add to it the acceleration of the arm, you can achieve a high rate of arm speed. There are two contributing factors that will increase the rate of arm speed: the length of the forearm and the faster the acceleration of the arm by fast twitch muscle fibers. As the shoulder begins to rotate through the release of this torque, the combination of musculature, length of the forearm, and arm angle will contribute to the increase in velocity. The faster the arm travels through the created acceleration phase, the faster the pitch will be. Genetics largely dictates this process. If a person has a predominance of fast twitch type 2 muscle fibers and has longer skeletal levers, for example, taller pitchers generally have longer arms, then an increase in velocity will result. It is imperative that the front leg does not collapse and bend beyond 120 degrees. If this occurs, you will lose energy from the back leg drive and the torso rotation. The body needs an axis or a pivot point to rotate. The front hip provides this axis in which the body can achieve maximum rotation and aid in velocity. If you collapse the front knee, this process will be diminished. You can still maintain power if the leg extends, as some of our models do, but there will be more of a challenge to keep the ball down in the strike zone.